It's question show time. Your questions, my answers, wherever you are on the channel. Question pops in your brain, write it down, I'll gather them up, and I'll answer them here. All right, let's get into it. Rafael Rodriguez. Question: why do almost all exoplanets found have such a short period to orbit their parent star? 10 days, 15 days, etc. when our solar system is so different? So after the test video, we got a bunch of questions like that. People wanting to know, why are all the planets that we're finding, these hot Jupiters, hot Neptunes, hot super Earths, stuff that orbits very quickly? And the reason is because with TESS specifically, it hasn't been operating for very long. It's only been going for a year. And think about the way TESS works, right? It looks at one spot in the sky for 27 days. Then it moves to the next spot in the sky for 27 days, then the next spot, finishes the entire southern hemisphere, and then it shifts to the entire northern hemisphere. So the total amount of time that TESS is looking at any spot in the sky is about 27 days. And so for TESS to make 3 observations of any world has to happen within 27 days. The chances are very, it's only going to find those planets that are orbiting really, really quickly, every couple of days. But over time, right, after TESS finishes the northern hemisphere, it's going to go back to the southern hemisphere, it's going to go back to the northern hemisphere. Also, it's producing all of these individual transits. It's noticing all these dimming of the light, and that's being pushed off to other astronomers who are then doing follow-on observations. And over the months and years, like think about what it'll take to find another Earth. You need to see a star dim once, and then you have to wait 365 days, and then you have to watch it dim again, and then you think you've got a planet. Then you've got to watch it dim 365 days later, and now you've confirmed a planet. That's 3 years of observations. TESS has only been going for 1 year, so it can't make 3 years of observation in only 1 year. And because it's only observing one quadrant at a time, it's going to take decades to fully map out the entire sky for 3 full years. So TESS is going to turn up a bunch of candidates, and over time, as it observes longer, we're going to start to see more and more of these planets with longer transit times, and therefore worlds that are more like our sun. So be patient, give it some time. Garrett Claiborne. What about laser highways? They should be able to do constant 1G thrust. So this was back on the QA where we talked about why we can't have any constant 1G acceleration, because you would need to turn the entire universe into chemical rocket fuel, and you still wouldn't be able to have 1G for longer than a couple of weeks at the most. So so the idea of laser highways is you've got a bunch of laser systems that are organized from here to the nearest star, and you've got a spacecraft that gets accelerated from one laser to the next laser to the next laser, and they just keep accelerating you. And then once you've reached the halfway point of your journey, then the lasers decelerate you back down to your place, to your destination. But to imagine the infrastructure that it would take, you would need to have, because you're talking about constant acceleration the whole time. Not just a single kick to get you up to 10% the speed of light and then you coast, but you need lasers placed every few hundred astronomical units all the way between us and the nearest star. And think about the orbits, they're all going to be moving around. So you need a whole galaxy filled with lasers that are constantly shooting at different, so that is a big infrastructure project to get that working. So I don't think we're going to see that in our lifetime. Tim Robinson. Robert Zubrin calls the Lunar Gateway the lunar toll booth, and it says it reduces our mission options. What are your thoughts? I dare not disagree with Dr. Zubrin. I might have mentioned this before. Robert Zubrin is one of my greatest inspirations, one of the people that helped get me excited about space exploration in the first place. I read The Case for Mars, and it blew my mind. Right? Here we were looking at the space shuttle program, and Robert Zubrin is laying out this plan to be able to send humans to Mars within a decade for a few $1 billion, and it was just total game changer. And it was an influence for Elon Musk and an influence for Jeff Bezos, and it totally changed NASA's thinking about the way that they will be doing human missions to Mars. A lot of in situ resource acquisition, so that they're going to go to Mars and they're going to gather up supplies on the surface of Mars and use that as a way to bring humans back. The lunar gateway is this spot that's mostly out of the influence of the Earth's gravity well, that you may need like 4.5 kilometers per second to get from Earth orbit to Mars, but if you can get up to a high lunar orbit, then you'll need about 1 kilometer per second to get to Mars. So there is value in having a station that is at this place. As well, you can do orbital refueling. You fill up you get to orbit, fill your fuel tanks, get up to the lunar gateway, fill your fuel tanks, and then you can take gigantic payloads to Mars. So there are good reasons to do it. I think if you just are absolutely set on sending humans to Mars, then I think it makes sense to just do the straight launch. Launch from Earth, go to Mars, land on Mars, build up their infrastructure, do that. And if you want to go to other places, then the Lunar Gateway kind of makes sense. But really, the Lunar Gateway exists as a way to deal with various White House administrations changing their minds. We're going to the moon. We're going to Mars. We're going to go to an asteroid. No, we're going back to the moon. No, we're going to Mars. And so you could see NASA kind of going, okay, we need to be able to provide some solution that allows us to weather these changes in goals over time. And that's what the Lunar Gateway is. It is a place that is farther away from Earth, that gives future White House administrations and Congress more options on places they want to visit in the solar system without necessarily building all the infrastructure for a Mars program and then having that scrapped, and building all the infrastructure for a moon program and then having that scrapped. So the Lunar Gateway is a political compromise, and considering how things have changed, I think it's a very rational political compromise that the people who are working at NASA have proposed to be able to deal with that. And yeah, if you had the will and the mindset and the funding to accomplish huge missions to Mars, then that makes a ton of sense. But until then, politics being politics, people need to try to figure out a way to keep moving forward in dealing with a fairly complicated political system. So that's why I think it happens. Bill Sugden. Hey Fraser, we know the physiological problems caused by microgravity, and I used to think that an experimental rotating space station could be used to check out how much gravity is required for human health. However, as there are plans for long-term occupation of the moon, could this give us some ideas about minimal gravity requirements for astronauts? Right. One of the questions that we have today is, what is the impact of lower amounts of gravity, say lunar gravity or Martian gravity, on human beings over long periods of time? And the answer is we don't know. We know that microgravity causes all kinds of problems on the human body over time that you have to deal with using exercise for long periods of time, and some of them you can't account for. But we don't know if 15% gravity on the moon, 35% gravity on Mars is going to be enough for a human being to get by. A rotating space station is sort of the best way because you can change the gravity. So you can rotate faster or slower, and you can spend a year in half gravity, a year in 3/4 gravity, and you could literally dial in what is the minimum amount of gravity that's required. And if it turns out that the minimum is somewhere between the moon and Mars, then we know that people can live on Mars, but they can't live on the moon. So if we have a long-term space station on the moon, we won't know if that's enough to live on Mars. So really, it's got to be Mars. And I think it's really got to be that rotating space station like you said originally. Computer Bladed. Couldn't Titan be Earth in 3 billion years when the sun expands? Right, so as the sun is dying and it moves from its main sequence phase into its red giant phase, it's going to expand out. It's going to gobble up Mercury, gobble up Venus, maybe gobble up Earth, or throw it farther out into space. And its habitable zone, the habitable zone around the sun, will extend outward and probably get to the point where the moons of Jupiter will melt and they'll become these water worlds. And same thing with Saturn. It's an amazing idea to imagine that we could go to Titan and it would be, now the atmosphere is thick and the temperature is fine. So for a little while there, Titan will be this really fascinating place that we could go. Now, I'm not sure exactly where the habitable zone will be, and as the sun is in that final red giant phase, things aren't going to remain in any one place for very long. It's going to move through the final phases of its life before it finally, it's going to shrink down, expand back up, shrink down, slough off outer layers, and then eventually shrink down as a white dwarf star, and then it'll be dead. So there might be moments periods of, say, a few million years where Titan is habitable and then it's not habitable again, and everything freezes over again and then it's habitable again. So I think it's better to just hang out on Earth and maybe figure out a way to move Earth farther away from the sun as the sun continues to expand and get hotter. Duck goes quack. Could Mars colonists do their outdoor work at night so they get less radiation from the sun? And how much of a difference would that be? We've talked about how bad Mars is to live on, and there's really two reasons why. One is the radiation and the particles, the charged particles that are coming from the sun. They're blown by the solar wind. And they don't really have anything to do with whether the sun is in the sky or not, but they have to do with just, is Mars in the solar wind or not as it's turning? And so you could have a day where there's not a lot of bad space weather coming from the sun, or you could have a day when the space weather is really bad, but it might take a couple of days to get to Mars, so you won't really know. But the bigger issue is the galactic cosmic radiation, and this is the radiation that's coming from all directions across the universe, and it's hitting Mars, and that's the stuff that it's really hard to prevent against. That's the stuff that's going to cause cancer over the long term, and that it doesn't matter where, you cannot hide from it. It is coming from all directions. They are being generated by supernova and quasars billions of light years away, so it won't really help. You've got to stay underground. You've got to put a meter of ice and maybe some regolith on top of you and live underground, and every second that you spend outside on the surface of Mars, you gotta hurry and get back underground. Vortmax 1981. Question: how do we know the temperatures of the exoplanets? Is it something measured directly or based on models? It's both. Up until a couple of years ago, the only way that really astronomers knew the temperature of exoplanets was math, was models. So you knew how far away the planet was from its star, so you could calculate the amount of radiation, and you could tell whether or not there could be, say, liquid water on the surface of a planet, or whether, say, the surface is going to be 1,000 degrees centigrade because it's so close, and it's just models. But in the last couple of years, astronomers have able to make a few direct observations. Hubble has done it, and the Spitzer Space Telescope have done it, and they've been able to image just a couple of pixels and get a sense of what the temperature of the planet is, and use that as part of their calculations. But it's a brand new field, and over time, as the next generation of gigantic telescopes, the extremely large telescope, and of course James Webb, we're going to be able to make these direct measurements of exoplanet temperatures for a wide variety of systems, which is really exciting, because that is one of the ways that we'll try to get at whether or not these exoplanets are habitable or not. Mike Robertson. Hey Fraser, love the show. Does the gravity from the moon have any effect on satellites orbiting Earth? Yeah, absolutely. The sun, the moon, and all of the major planets, right, Jupiter and Saturn, they all have some kind of influence on the satellites that are orbiting the Earth. And of course, the moon's orbit is elliptical, Earth's orbit around the sun is elliptical, the various planets, sometimes we're close to Jupiter, sometimes we're far away from Jupiter, and they all actually do have an impact. And so what these do is they cause satellites to shift around in their orbits a tiny little bit. And for, say, geosynchronous satellites, this is really important, because you want your geosynchronous satellite to always remain exactly overhead so that it can broadcast that satellite television that you love so much. So the way they deal with it is they do something called station keeping. So all of the satellites have thrusters on board, and they're able to fire these thrusters to keep themselves in their perfect spot. And often the lifetime of a satellite depends on how much of this propellant on board they have to keep themselves on station until they run out of propellant, and then they drift away and they no longer can serve their purpose as a telecommunications satellite. And sometimes every other part of the satellite is still in perfect condition. All of its transmitters, receivers, its cameras, everything is working great, but it has run out of propellant and now it can't do its job anymore. And so actually people have worked out orbital repair satellites, things that can fly up to a satellite, bolt onto it, and continue to provide propellant, act like a second propellant system to keep the satellite in the right position so that it continue doing its job. So yeah, they're shifting around all the time. Everything is gravitationally influencing each other. Federico Fuidio. Where do you think we're going to find extraterrestrial life first? Mars, Titan, Europa, somewhere outside the solar system? That's a tough question. I think that we're going to find extraterrestrial life outside the solar system. I think it's going to be one of these gigantic new telescopes like James Webb or HabEx or LUVOIR, or some of the ground-based telescopes like the Extremely Large Telescope or the Magellan Telescope, and they are going to do spectroscopy of some planet. They're going to analyze the chemicals in the atmosphere of some planet orbiting out of the star, and they're going to detect some kind of biosignature. And we've done lots of episodes about this. There's going to be like methane in the atmosphere of some world, or they're going to see the red edge, which we talked about just a little while ago, and they're going to make some kind of detection. But the problem is that all we're going to know is that there's some kind of life there. Something's there, but we won't have any details. While, say, if we find life on Mars or Titan or Europa or Enceladus, we can actually analyze it. We can bring samples home. We can dissect it. We can put them in some kind of environment and see how it reacts. We can analyze its DNA. So finding life closer to Earth would be incredibly useful because then we can study it. While we detect that there's life at some planet that's 10 light years away, and all we know for the longest time, until we're able to actually send a spacecraft there, is that it exists. So I think that would be kind of heartbreaking, but I think that's where the first discovery will be made. Jeff Horn. I have a question for you, Fraser. We talk about look back time all the time, but we very rarely talk about what is actually out there in real time. Is there a field of study that focuses on, say, what's happening with galaxies and quasars that are billions of light years away right now versus look back time? Surely there are some surprising things that we could discover. The problem is that we have no way to know what's happening in those places, right? As we look out into space, the farther we look, the further we're looking back in time. You look a billion light years away, you're looking a billion light years back in time. And there's no way to know what these things are doing. And all we can do is make assumptions. So we look at the galaxies that are closest to us. We look at the stars that are closest to us and see how they behave. And then we assume that that's what's going on out there in other places across the universe. But we can never know unless we're willing to wait a billion years to watch a galaxy that is a billion years younger than what it really is today to evolve into its current form. The fact that we get to be able to see back in time is this wonderful gift to astronomy, because it allows us to see how those first building blocks of the universe came together. But the downside is that we don't see what anything looks like today unless it's really close to us. And there's no other way to know. So unfortunately, I'm not sure how we could do this unless we could figure out a way to see faster than the speed of light. Francois Morin. Hi Fraser, I hear that SO2 orbits the black hole at the center of our galaxy every 16 years. Could we predict when this star or others will collide or be swallowed by a black hole? Any chance that I could witness this event? Astronomers use very sensitive, very large telescopes to be able to perceive the supermassive black hole, the region around the supermassive black hole at the heart of the Milky Way. They need some of the biggest telescopes that have ever been built that use infrared radiation to be able to peer through the gas and dust to be able to see that region. And they can see stars and gas clouds and things like that are interacting in the environment around the supermassive black hole. But the reality is that you could smash all kinds of stars into the black hole. Our black hole could turn into a quasar, which is some of the brightest objects across the universe, and we wouldn't even see it, right? It wouldn't even be visible in our night sky as a bright source, even if it was as bright as a quasar that we see in other places. And it's just because it is so far away, and it is shrouded by gas and dust. So unfortunately, no matter what happens to the supermassive black hole, you would never be able to see it. Even if it doubled in brightness, tripled in brightness, went 75 times as bright, you need very special instruments to be able to see it. All right, that's it for this week's question show. Super fun, as always, wherever you are. Question pops in your brain, write it down. I'll gather them up, and I'll answer them here. I will see you next week.